So we have 9 people traveling in 2 taxis, and which is good because we know we're going to be dividing a subset of 9 into 2 different vehicles. That's what these things are here. But basically, so we have 2 taxis, 9 riders. What we need is the number of riders per taxi, and from there we could compute the number of different ways that they can be arranged. Until we know how many are going in each one, we can't do that. Statement 1 tells us that the larger of the 2 taxis can hold no more than 5 people, so 5 is the max there. The problem actually said that they have different passenger capacities, so this one, the smaller one, is smaller and different. In order to be smaller and different, it has to have 4. I guess it could have 3, but then we wouldn't have enough room for all 9 people, so it has to have 4. So we would use our combination formula, n factorial over k factorial times n minus k factorial, where n would equal 9 here, the big group, and k would equal the subgroup. We would only need to run it for either 5 or 4, that would be the total number of combinations, because all the rest of the people would just go in the other taxi. So statement 1 is sufficient. We cross off B, C, and E. Statement 2 tells us the smaller of the 2 taxis can hold no more than 4. So let's just pretend like we just found out that 4 go in the small taxi. The large taxi, though, we don't know how many go in here, and it makes a big difference. If 5 people go in there, then it's, exactly what we just figured out for statement 1. What if it's a huge taxi? It's a minivan or a bus or something. What if 10 people can go in there? Then you have a whole bunch of different combinations, including all of them going on the big taxi and none of them going in the small one. So without knowing how many people can go in each of the 2 taxis, statement 2 is insufficient. We cross off D and select A.